Hello and welcome to my video on proof by mathematical induction. To begin with, we'll start with probably the simplest problem you'll see, and then we'll move on to a harder problem. So here is our problem. We're trying to prove that 1 plus 2 plus 3 and so on until the value n is equal to n times n plus 1 over 2 for all values greater than or equal to 1. Our first step is to prove that the function works for n is equal to 1. So we start by creating a premise or a proposition P, and we split the two sides into the left-hand side and right-hand side. So when n is 1, the left-hand side, this side, is simply 1, as n is the first term, which is just 1 plus 0. The right-hand side is this equation just here, and we can substitute 1 in for n. And then when this is simplified, we get 2 over 2, or 1. You'll notice that this is the same as our left-hand side, so the right-hand side equals the left-hand side, and therefore, proposition 1 is true. Now, we make an assumption, and this is where the whole proof comes from. We must assume that pk is true for the same conditions, where k is true for all k's greater than or equal to 1. By the way, this symbol here means for all if you didn't know. Sometimes maths can look more difficult than it is, so if you see this, don't panic, it just means for all. Anyway, we essentially sub k in where n is and say it is true as such. And now we prove p k plus 1. So for the right hand side, where we see k in step 2, we replace it with k plus 1. After rearranging, we get k plus 1 times k plus 2 over 2. And then for the left-hand side, we have 1 plus 2 plus 3, and so on until k, and then we add k plus 1. Now this is where our assumption comes in. We know based on our assumption here, that for values up to k, the function is equal to k times k plus 1, all divided by 2. So we just add k plus 1 to that function, and get this. Now we make it part of the same function by multiplying it by 2, so that the value remains the same as the two 2's cancel out. Now, because we have the same terms in the brackets, we can take out the common factor of k plus 1 and multiply it by the sum of the terms outside the brackets, k and plus 2, to get k plus 1 times k plus 2 divided by 2. And now you'll notice this is the same as our right hand side, which means that proposition k plus 1 is true, assuming pk is true. Therefore, by principle of mathematical induction, Pn is true for all n's greater than or equal to 1. Here is another problem which is much more complex, where Pn is equal to 1 times 2 plus 2 times 3 plus 3 times 4 and so on until we get to n times n plus 1, which we're trying to prove is equal to n times n plus 1 times n plus 2 all over 3. If you are feeling confident, pause the video and have a go yourself. Assuming you have had a go, if you wanted to, I will continue. So we know from before, we start by proving the statement for n equals 1. This is proposition 1 or P1, which on the left hand side is just 1 times 2, or 2. For the right hand side, we have 1 times 1 plus 1, which is 2, which is multiplied by 1 plus 2, which is 3. All of this is divided by 3. So we get 6 over 3, which is, of course, 2. Left-hand side is equal to the right-hand side, and proposition 1 is true. Now, we assume that pk is true, as we did before, such that when we sub in k where n was, we get this. Now, using this, we solve for k plus 1. Let's do the right-hand side first. So we sub in k plus 1 every place we see k, and then simplify. So we've subbed in k plus 1. We simplify to get k plus 1 times k plus 2 times k plus 3 divided by 3. We can then expand these brackets. We can then expand these brackets out, which I'm assuming you can do if you are doing PMI, but if not, go and look at how to do this because it's an important skill. So we expand the first brackets as such. We then expand this new bracket here with k plus 3 to get k cubed plus 6k squared plus 11k plus 6 over 3, and this is of course our right hand side. Now the left hand side. So we know that the left hand side is what we have up to k, and then we just add k plus 1 times k plus 2. So we add k plus 1 plus k plus 2 to the left hand side from proposition k. Ek was assumed to equal this, just here. So we can add k plus 1 times k plus 2 to this as such. K plus 1 times k plus 2 can be expanded to equal k squared plus 3k plus 2. This can then be moved to the top of the function by multiplying it by 3 to cancellate the denominator here of 3. We can expand these brackets out. So here we are. And then again we simplify, and voila, there we are. We get our right hand side, which if we compare the two sides, they are equal to each other. And we have proved the problem using PMI. Thanks for listening. Hopefully this helped.